Welcome back to Weapons Science. Imagine standing next to the most advanced spy plane ever built, only to see highly volatile jet fuel pouring directly out of its wings onto the concrete. It looks like a catastrophic system failure, a multi-million-dollar disaster waiting to ignite. But what if I told you this terrifying leak was actually designed by genius engineers? The ground crews at Beale Air Force Base didn't panic when they saw these growing puddles. They knew that the SR-71 was a mechanical paradox. To survive the brutal, unforgiving environment of Mach 3 flight, this legendary aircraft had to remain fundamentally broken on the ground. Its very survival depended on its ability to leak. Critics of the era called it an engineering nightmare, questioning how a nation could spend billions on a plane that couldn't even hold its own fuel before takeoff. Yet, the physics of thermal expansion dictated this exact radical compromise. Let's peel back the titanium skin of the Blackbird to understand why this leak was a stroke of absolute genius. If Lockheed's legendary skunkworks team, led by the brilliant Kelly Johnson, had sealed these fuel tanks perfectly on the ground, the Blackbird would have torn itself to pieces within minutes of reaching its cruising speed. The secret lies in a battle against extreme heat, materials science, and a fuel so stable it defies logic. In this deep dive, we are going to explore the limits of Cold War aerospace engineering. We'll look at the extreme friction of Mach 3 flight, the covert operation to smuggle titanium from the Soviet Union, and the mind-bending chemistry of JP-7 fuel. This is the untold story of why the fastest plane in history had to leak. To understand the leak, we must first understand the environment the SR-71 was built to conquer. Flying at over 80,000 feet and speeds exceeding Mach 3.2, the Blackbird didn't just fly through the atmosphere. It collided with it, compressing the air in front of it to a violent degree. At these extreme speeds, aerodynamic friction becomes a thermal barrier. The kinetic energy of the air molecules hitting the airframe is converted directly into heat. The nose of the aircraft would reach temperatures of 800 degrees Fahrenheit, while the engine nacelles glowed at over 1,000 degrees. This wasn't a temporary spike in temperature. During a typical mission, the Blackbird would sustain these blistering temperatures for hours. Standard aviation materials like aluminum, which lose their structural integrity at just 350 degrees Fahrenheit, were completely out of the question. If built with traditional aerospace metals, the wings would have sagged, the control surfaces would have seized, and the airframe would have suffered catastrophic structural failure. The skunkworks engineers needed a material that could thrive in a furnace. They needed a miracle metal. The search for this miracle metal led them to titanium. Titanium possessed the perfect strength-to-weight ratio and could withstand temperatures that would melt aluminum. But in the late 1950s, the United States had a massive problem. They didn't have enough titanium to build a single plane, let alone a fleet. The world's largest exporter of high-grade titanium at the time was none other than the Soviet Union, the very nation the Blackbird was being built to spy on. To solve this, the CIA established a network of dummy corporations and shell companies to purchase the raw ore from Soviet suppliers, completely undetected. The Soviets unwittingly sold the United States the very material that would be used to build an unshootable spy plane. This smuggled titanium alloy, designated Beta 120, was incredibly difficult to work with. It was so hard that traditional steel drills and fabrication tools would shatter upon contact. Lockheed had to invent entirely new manufacturing techniques. They designed drills tipped with diamonds, used gold-plated screws to prevent galvanic corrosion, and threw out standard workshop tools because even the chlorine in tap water could cause the titanium to fail under stress. The extreme chemical sensitivity of titanium meant that even the acid from a worker's hand could compromise a weld. Every single component had to be acid-washed, handled with specialized gloves, and welded inside hermetically sealed chambers filled with inert argon gas to prevent oxygen contamination. But even after mastering the fabrication of titanium, the laws of physics presented an even greater challenge: thermal expansion. When metals are heated, their atoms vibrate more violently, pushing them further apart and causing the entire structure to expand in volume. At Mach 3, the SR-71's titanium skin would expand by several inches in both length and width. If the aircraft had been built with tight, rigid joints on the ground, this expansion would have generated unimaginable internal stresses, causing the metal panels to buckle, warp, and violently rip the airframe apart. To prevent this, Kelly Johnson and his team made a radical decision. They didn't fight thermal expansion, they embraced it. They designed the Blackbird with loose, overlapping expansion joints On the ground, these joints had visible gaps, allowing the metal panels to slide over one another. As the aircraft accelerated and heated up in flight, the titanium panels would expand, closing these gaps completely. The skin of the aircraft would become smooth, rigid, and perfectly sealed only when it was flying at its design speed of over 2,000 miles per hour. This solution, however, created a massive complication. The fuel tanks of the SR-71 were not separate, isolated bladders inside the wings. To save weight and maximize fuel capacity, the outer titanium skin of the wings and fuselage served as the actual walls of the fuel tanks. Because the titanium skin had to expand and contract, any sealant used in the joints had to be incredibly flexible. But in the 1960s, there was no synthetic rubber or sealant in existence that could survive both the freezing cold of high altitudes and the blistering 1,000-degree heat of Mach 3. The engineers tried to develop specialized sealants, but they all failed after a few thermal cycles. Left with no other choice, Kelly Johnson accepted the compromise. The fuel tanks would simply have to leak when the plane was cold on the ground. It was a design feature, not a bug. For the ground crews, this meant working in a constant state of dampness. The Blackbird would sit on the tarmac, dripping fuel from dozens of weeping seams. The hangar floors had to be constantly managed with drip pans and specialized absorbent materials to prevent a hazardous accumulation of fuel. This brings us to the peak engagement moment of our story, the magic of the fuel itself. If the Blackbird leaked standard jet fuel like JP4 or commercial kerosene, the hangars would have been ticking time bombs. A single spark from a tool or a static discharge would have caused a catastrophic explosion. To make this leaky design safe, the military had to develop an entirely new class of fuel, JP7. JP7 is a highly specialized hydrocarbon mixture with an incredibly high flash point and low volatility. It is so stable that it is virtually impossible to ignite under normal atmospheric conditions. In a famous demonstration of its stability, engineers would take a burning match and throw it directly into a puddle of JP7 fuel. Instead of a massive fireball, the match would simply sizzle and go out smothered by the liquid fuel. The fuel was safer than the water in some municipal systems. JP7's unique properties were achieved by carefully blending fluorocarbons, high molecular weight hydrocarbons, and specialized lubricants. It contained almost no volatile light-end hydrocarbons, meaning it did not produce flammable vapors at room temperature, even when spilled over a wide area. But this extreme stability created a new problem. How do you ignite a fuel that refuses to burn? Standard spark plugs were completely useless inside the Blackbird's massive Pratt & Whitney J58 engines. The fuel simply wouldn't catch fire from a simple electrical arc. The solution was triethylborane, or TEB. TEB is a highly pyrophoric chemical, meaning it ignites spontaneously the moment it comes into contact with oxygen. The SR-71 carried a small, pressurized tank of TEB specifically to start the engines and light the afterburners in flight. When the pilot pushed the throttles forward, a small dose of TEB was injected into the combustion chamber. The chemical would explode into a brilliant green flame, which then heated the surrounding air and JP7 fuel enough to initiate and sustain stable combustion. Because of this leaky design and the weight of the fuel, the SR-71 could not take off with full tanks. Taking off with a maximum load of JP7 would put immense stress on the landing gear and structure, and the fuel would leak at an unacceptable rate while taxiing on the runway. Instead, the Blackbird would take off with only a partial fuel load, just enough to safely get airborne and climb to a moderate altitude. Once in the air, the pilot would accelerate to supersonic speeds, allowing the airframe to heat up, expand, and seal the fuel tanks completely. Once the tanks were sealed, the pilot would slow down and rendezvous with a specialized tanker aircraft, the KC-135Q. This tanker was specifically modified to carry and pump the highly specialized JP7 fuel, keeping it isolated from the tanker's own standard aviation fuel. This mid-air refueling dance was one of the most demanding tasks for both the Blackbird pilots and the tanker boom operators. The SR-71 had to fly at its absolute lowest limit of speed and stability, while the heavily laden tanker flew at its maximum performance limit. Once connected, thousands of gallons of cold JP7 would pump into the warm, expanded tanks of the Blackbird. This cold fuel would cause the titanium panels to contract slightly, sometimes causing minor leaks to temporarily reappear until the aircraft accelerated back to Mach 3. With its tanks topped off, the pilot would disconnect from the boom, light the afterburners, and rocket back up to 80,000 feet. Within minutes, the friction would heat the titanium back up, locking the expansion joints tight and turning the plane into a seamless, high-speed spy platform. The SR-71 Blackbird operated for over 3 decades without a single aircraft being lost to enemy fire. It flew higher and faster than any surface-to-air missile could track, rendering Soviet air defenses completely obsolete. It was a triumph of analog engineering in an era before supercomputers. Kelly Johnson's team designed the entire plane using slide rules and drafting boards. Every curve, every joint, and every chemical compound was calculated by hand. They didn't have advanced digital simulations to predict how the titanium would expand. They had to rely on pure physics and intuition. Today, the SR-71 still holds the absolute speed record for a manned air-breathing jet aircraft set back in 1976. It is a record that may never be broken by a conventional aircraft. The leaky spy plane remains an icon of what humanity can achieve when pushed to the absolute limits of possibility. The story of the Blackbird's leaking fuel tanks is a powerful lesson in compromise. In the world of high-performance engineering, there is no such thing as a perfect design, only a series of calculated trade-offs. To build the fastest plane in the world, the engineers had to let it leak. If you enjoyed this deep dive into the engineering secrets of the Cold War, make sure to hit that subscribe button. We have plenty more stories of incredible military technology and scientific breakthroughs coming your way. Let us know in the comments, what engineering marvel should we cover next? Now let's look at another military mystery. Why does the US Navy intentionally sink its own active aircraft carriers? It seems counterintuitive to destroy these multi-billion-dollar symbols of American power, but these controlled sinkings are actually the ultimate test of survival. Known as shock trials and weapons effect tests, these operations involve detonating high explosives near or directly against the hull of retired carriers. By observing how the structure absorbs the shock waves, engineers can design future ships to survive real-world missile attacks. Every square inch of the carrier is packed with sensors, cameras, and structural monitors. The data gathered from these controlled sinkings is classified, but it directly influences the steel alloys, compartment layouts, and damage control systems used in the new Ford-class supercarriers. Next, let's shift from the sea to the land. Why does the M1 Abrams main battle tank use an insane gas turbine engine instead of a reliable diesel engine like almost every other tank in the world? The answer lies in pure, unadulterated power-to-weight ratio. The Honeywell AGT 1500 gas turbine engine produces 1,500 horsepower, allowing a 70-ton tank to accelerate like a sports car. It is whisper quiet compared to a diesel engine, earning the Abrams the nickname Whispering Death during its initial deployment. But this performance comes at a cost. The turbine consumes fuel at an alarming rate, even while idling. It can run on almost any liquid fuel, from diesel to jet fuel to perfume, but its thirst requires a massive, complex logistics tail to keep the tanks supplied in combat. Moving back to the skies, why is the F-22 Raptor legally banned from being sold to even the closest U.S. allies like Japan or Israel? The Obey Amendment, passed by Congress in 1997, ensures that the F-22's revolutionary stealth technology remains a closely guarded American secret. The F-22's radar cross-section is reportedly the size of a marble. The U.S. government feared that if the aircraft were exported, foreign adversaries could reverse engineer its radar-absorbent materials or study its electronic warfare suite, compromising America's air dominance. Even when the production line was shut down, the tooling was carefully preserved and locked away rather than sold. The F-22 remains a pure air superiority fighter, a weapon too powerful and too secret to be shared with anyone else in the world. Finally, how has the U.S. Air Force kept the Cold War-era B-52 Stratofortress flying for over 70 years, with plans to keep it active past its 100th anniversary? The B-52 is a rugged, over-engineered masterpiece that has outlived its intended successors. Unlike modern stealth bombers, which require air-conditioned hangars and delicate maintenance, the B-52 is a simple, heavy metal truck. Its airframe is incredibly durable, allowing it to carry a massive variety of weapons, from conventional gravity bombs to advanced cruise missiles. With constant engine upgrades, modern radar systems, and digital cockpit retrofits, the B-52 remains highly cost-effective. It is cheaper to operate than any modern bomber, proving that sometimes classic analog engineering is impossible to beat. But not every high-tech project succeeds. The Zumwalt stealth destroyer was supposed to be the future of naval warfare, but instead became an $8 billion floating failure. Its advanced gun systems were designed to fire GPS-guided shells that cost nearly $1 million each. Because the Navy cut the order from 32 ships to just 3, the cost of the ammunition skyrocketed. The guns became completely unusable because the Navy could not afford to fire them, leaving the stealth destroyer without its primary weapon system. The Zumwalt serves as a cautionary tale of over-engineering and runaway procurement costs. It proves that even the most advanced technology is useless if it is too expensive to operate in the real world, a lesson that Lockheed's Skunk Works understood perfectly. Let's return to the metallurgy of the SR-71. Titanium is notoriously difficult to refine from its raw ore. The Kroll process, which uses magnesium to reduce titanium tetrachloride, requires extreme temperatures and a completely inert atmosphere to prevent the metal from absorbing oxygen. If even a tiny amount of oxygen or nitrogen enters the refining process, the titanium becomes extremely brittle. This brittleness can lead to microfissures that are invisible to the naked eye but catastrophic under the high-pressure environment of supersonic flight. To ensure absolute quality, Lockheed established an unprecedented inspection regime. Every single batch of titanium delivered to the Skunk Works was subjected to ultrasonic testing, X-ray analysis, and chemical spot testing before it was allowed near the assembly line. The physics of aerodynamic heating are counterintuitive. Most people think the heat comes from the air rubbing against the metal's skin. While boundary layer friction does play a role, the vast majority of the heat actually comes from the compression of the air in front of the aircraft. This is known as the stagnation point. When air is forced to stop or slow down rapidly as it hits the leading edges of the wings and nose, its kinetic energy has nowhere to go but to convert into thermal energy, raising the local temperature to extreme levels. The boundary layer of air sliding along the fuselage also heats up, creating a thermal blanket that prevents the aircraft from cooling itself. The only way to keep the internal electronics and pilots from cooking was to use the fuel itself as a heat sink. Yes, the JP-7 fuel was actually used as a coolant. Before reaching the engines, the cold fuel was pumped through a network of heat exchangers surrounding the cockpit, landing gear bays, and delicate camera equipment, absorbing the heat and keeping them functional. This preheated the fuel, which actually improved its combustion efficiency once it reached the engines. It was a brilliant closed-loop system. The heat that threatened to destroy the aircraft was harvested to help power it through the sky at Mach 3. The Pratt and Whitney J58 engines were engineering marvels in their own right. They were designed to operate continuously in afterburner mode, a feat that would destroy modern fighter engines in a matter of minutes. At high speeds, they functioned as hybrid turbo ramjets. At Mach 3, a series of bypass tubes would redirect the incoming air around the compressor stages directly into the afterburner. This bypassed the delicate spinning blades, turning the engine into a highly efficient ramjet and allowing the aircraft to maintain high speeds. To control the airflow into the engines, the J58 utilized massive, movable inlet spikes. These spikes would translate backward by up to 26 inches as the aircraft accelerated, capturing and slowing down the supersonic shockwaves to subsonic speeds before they hit the compressor. If the spike failed to position itself correctly, the shockwave would be expelled from the inlet, a violent event known as an unstart. An unstart would cause an immediate loss of thrust on one side, violently yawing the aircraft and testing the limits of the pilot's control. Because of the extreme altitudes and temperatures, the pilots had to wear full-pressure suits that were virtually identical to those worn by astronauts. If the cockpit depressurized at 80,000 feet, their blood would literally boil without these specialized suits. The suits were also connected to a robust cooling system. While the outer windshield of the cockpit was hot enough to bake a steak, the pilot sat in a comfortable, air-conditioned microenvironment, insulated from the blistering heat of the titanium skin just inches away. The primary mission of the SR-71 was reconnaissance. It carried advanced high-resolution cameras that could photograph over 100,000 square miles of the Earth's surface in a single hour. The quartz glass windows for these cameras had to be completely distortion-free. But how do you prevent the camera windows from warping under the extreme heat? The engineers fused the quartz glass directly to the titanium frame using ultrasonic welding. This prevented any optical distortion, allowing the cameras to capture incredibly sharp images from 80,000 feet. The matte black paint of the SR-71 wasn't just for aesthetics. It contained microscopic iron ferrite particles that absorbed radar waves, reducing the aircraft's radar cross-section. This was one of the earliest applications of stealth technology, long before the F-117 or B-2. The dark paint also helped to radiate heat away from the airframe, keeping the internal structures slightly cooler. It was a dual-purpose design. Stealth and thermal management combined in a single, elegant coating that defined the iconic look of the Blackbird. Despite its incredible capabilities, the SR-71 was retired in the late 1990s. The rise of spy satellites, advanced unmanned aerial vehicles, and the massive operational costs of maintaining a dedicated fleet of tankers made the Blackbird too expensive to justify. Each flight required days of maintenance, intensive inspections, and a complex logistics network. The planes became hangar queens, requiring hundreds of maintenance hours for every single hour of flight. Yet no modern system has ever truly replaced its unique capabilities. A satellite's orbit is predictable, allowing adversaries to hide sensitive equipment when they know a satellite is passing overhead. But the Blackbird could appear anywhere in the world in a matter of hours, completely unannounced, and capture real-time intelligence before anyone knew it was there. Ultimately, the SR-71 Blackbird is a testament to human ingenuity. It represents a time when engineers dared to build the impossible, accepting radical, messy compromises like leaking fuel tanks to achieve unprecedented performance. It is a monument to what we can achieve. The legacy of Kelly Johnson and the Skunk Works team lives on in every modern stealth fighter and hypersonic research vehicle. They prove that sometimes the most elegant solution is the one that looks broken on the surface. The next time you see a leak, remember the Blackbird. Thank you for joining us on this deep dive into weapons science. If you want to support our channel and help us create more high-quality documentaries like this, please hit the like button, share this video with a physics nerd, and subscribe for more. This is Ethan Walker signing off. Stay curious, stay informed, and always look beneath the surface of the world's most advanced technology. We'll see you in the next episode, where we'll uncover more secrets of military engineering and scientific breakthroughs. Until next time, take care.